is the kind of situation you may encounter if you've read someone's paper, for example. You want to make a solution that they've described in their method. So they'll describe a solution that has multiple components, such as this one that has tris, magnesium chloride, EDTA, and you'll be needing to make it up with whatever you happen to have in your lab. So in our case, we've got a 0.5 molar solution of tris, 100 millimolar solution of magnesium chloride, 20 millimolar solution of EDTA. So yeah, those are our ingredients that we have.
Those are our ingredients. So we need a recipe.
Yeah.
Yeah. And as you said, Alice, it's really important to realise that pretty much all the solutions that we deal with in biochemistry are multi-component. So they are solutions which contain lots and lots of different types of chemical, all in different concentrations. So as usual, Alice's first step is going to draw a picture. Really give ourselves a lovely anchoring, a lovely frame of reference, something that we can start riffing numbers around. And you know, what Alice is doing here is just reminding herself of what's going in here. Now, of course, in addition to these ingredients, we've also got water. This 500 mils is going to be made up by mixing these stock solutions in small amounts, but making up the volume with water to 500 mils.
I'll just put a question mark, just in case somehow the solutions add up to 500.
Well, they might. Yes, that's true. We could,
just in case.
Yep.
Unlikely, but possible. So, yeah, these are the solutions we have. And so, in the end, we want this ingredient here, the 0.5 molar tris, eventually has got to give something that's 50 millimolar. Yep.
So what's your next
So
step?
With the different components, we'll need to take them step by step. So we'll just start with the tris. So we have, we have 0.5 molar, and we need 50 millimolar.
So would you at this stage maybe be tempted to re-express this number so that it's in millimolar? So maybe call that 500 millimolar.
Yeah.
And then it becomes really clear, doesn't it, that there's a very neat relationship between these two numbers. One is 10 times the other. And really good to be on the lookout for these lovely, neat relationships, because they're essentially really easy to understand fractions, in this case 1 in 10, and the posh word for fractions when we're dealing with this type of multi-component solution with the stock solutions and the final product would be a dilution factor. So we would say in this case that we need a dilution factor of 10 to go from the stock to the final. So if the final is 500 mils, we would need.
So we need a tenth. If we want a dilution factor of 10, then to add to a total volume of 500, we'd have 1/10 of that, which is 50 milliliters. I'm so used to milliliters of.
So we'll take 50 mils of 0.5 molar tris to get what we need here. So that's a really neat way of doing it. Lovely, easy dilution factor. But dilution factors can really get you into trouble if you get them the wrong way round. It's interesting that both Alice and I really gravitate to that as soon as we see these numbers. But let's do it longhand, because the longhand way is really, really important as well. So what's another approach here?
So going back to what we had before, we have 500 millimolar. We need 50 millimolar. So this is our stock solution, 50. Or rather, I want to figure out how much I need in.
Yeah, so we're asking the question, what quantity do we need? Yeah.
So I need 50 millimoles per liter, and that's just writing this out because it's a lot easier to see what we're working with when we expand out the notation.
In plain English.
Yeah, so in a liter, we need 50 millimoles. So again, can recognize that 1 litre is twice
Yeah.
what we need.
Again, it's there's a lovely fraction there, isn't there?
So
that
then we
that
need
500 mils is half a litre.
So we need 25 millimoles of tris,
tris, yep.
in there. So that's what we need in our solution.
Yeah. Somehow we've got to get 25 millimoles of tris into here.
Mm-hmm.
Okay.
So this is where we go back to what we have in our cupboard, which is the 0.5 molar tris, or 0.5. So this is what we have. 0.5 moles per litre. So writing that out. So we working in millimoles. So we can take that down using prefixes just to make it close to the scale that we're working in.
What I like what you've done there is you've aligned the prefixes. You've recognised that we need 25 millimoles. So you've said, can I re-express this solution here? So I'm actually saying it's a certain number of millimoles per mil, and it's 0.5 millimoles per mil. We need 25. If we need 25 of something, and every mil contains 0.5, we're going to need 50. So it's going to come out at exactly the same number. And what I love about this is that we've done it 2 completely different ways. We've done one way where we're following the quantity, and we've done another way where we're doing a simple dilution factor, but they've come out to be absolutely equal. And that really gives us massive confidence that we've got the right answer. So it's a really, even if you're very, very nimble and you're very fluent with the dilution factors, or even if you like to take the more long-winded, very safe, quantity-based approach, then doing it both ways is a really fantastic way of not only building the fluency, but also checking that you've got the right answer. So we could do that with the other ones as well, couldn't we? We could either think about the dilution factor that we need in going to 5 from 100, so that's a 20-fold dilution there. Or we could think about the dilution factor that we need to get to 1 from 200. It's again a 20-fold dilution. But we won't do that because I think that's a great thing for everybody to have a go at. You've got 2 different strategies there. The one strategy that we're not teaching you and not encouraging you to do is not to use rote-learned equations. That's really something that we would strongly recommend that you don't do. Also known as plug and chug, because it really it is very disempowering. You often end up not knowing what goes on the numerator, what goes on the denominator. It can get very, very messy, and it's very, very difficult to unpack what happens. And what is even worse is to use the plug and chug with the scientific notation, because then not only have you got all these numbers that you don't know how they've been formed, but you've got no idea what the magnitude is. You've got no perception of whether these numbers are sensible. If you start expressing these as 100 times 10 to the minus 3 or 20 times 10 to the minus 3, I can't visualize that. So these are the strategies that you used, Alice. I think 2 different ways and some ways of not doing it as well.
Saves on memorizing formulae as
Yeah,
well. You can
that's
kind
right.
of think through what is happening, because this is all stuff that is tangible. So rather than making it into something abstract.
Well, one last thing which we didn't mention is that we're going to end up with maybe 50 mils. I can't remember what we said. There's a 1 in 20 dilution there, so it's 25 mils of that and 25 mils of that. So all that adds up there to 100 mils, but we need 500. So that's where we are going to need some water. Now, a perfectly acceptable answer would be to say that we need 400 mils of water, but there is a complication there, isn't there? What's that?
So if I'm not actually sure whether we need to pH this because
I think, well...
I think they're saying the component is
Oh,
pH
no.
7.5,
No, I think
right?
we will, because this EDTA here could be any pH.
Yeah,
I mean, and that's quite a strong buffer in itself.
that's true.
So adding that EDTA to this tris might take the pH away from
Yeah.
7.5. So whenever you're making a multi-component solution like this that needs pHing, you need to make sure that you make the volume up to less than the total amount, then do the pHing, and then finally make it up to 500 after you've done the pHing.
Otherwise, you'll go over.
Yep, you don't want to go over.